All right, so today we're going to talk about regression wisdom. So a lot of the things that we're going to cover today is like how do you interpret the data? So up to this point, we've collected data, we've organized the data in graphs and charts, we've done some math to kind of standardize the data, and we've even made an equation that can predict about what the data should be. Okay. So linear regression only works for linear models, which makes sense, but linear meaning a straight line, y equals mx plus b. Now, a curve relationship between two variables might not be apparent when looking at a scatter plot alone, but there will be more obvious plots. Though it'll be more obvious in the plot of the residuals. So remember, we want to see nothing in a plot of residuals. So let's look at this example. The scatter plot of the residuals against duration of emperor penguins dives holds a surprise. The linearity assumption says that we should not see a pattern, okay? But instead, there is a bend. Even though it means checking the straight enough condition after you find the regression, it's always good to check your scatter plot of residuals for bends that you might have overlooked in the original scatter plot. So the plot in red is just the actual scatter plot. And then when we look at the residuals, there's a pattern that seems to emerge, okay? So no regression analysis is complete without a display of the residuals to check that the linear model is reasonable. Residuals often reveal subtleties that would not be clear from the original data point. So remember, the residual is based on the distance from the original data point from the regression line. Sometimes the subtleties we see are additional details that help confirm or refine our understanding. Sometimes they reveal violations of regression conditions that require our attention. You might not call a residual plot or it says you might call, I said might not, but you might call the residual plot the judge. It has the final say in the linearity of the data. So basically, when we're considering the x variable, if it's a very short range or a short enough range, we can plot a linear plot, and the correlation can be fairly decent. But it might actually be a shorter span of maybe an exponential or a quadratic. So we don't really know for sure until you look at the residuals. The numbers don't lie, okay? So now let's look at this. It's a good idea to look at both the histogram of the residuals and the scatter plot of the residuals versus the predicted values of the regression predicting calories from sugar contents in cereal. So this is a couple chapters ago where we talked about this. So this chart here is just a histogram of the residuals, all right, with respect to the calories. And then this right here is the scatter plot of the residuals with regards to the predicted values, okay? So the small modes in the histogram are marked with different colors and symbols in the residual plot above. Do you see? What do you see is what they're saying. What do you see? Well, there's something there, right? So an examination of the residuals often leads us to discover groups of observations that are different from the rest. In other words, look at this. What are these guys doing over here? What are these guys doing over here? How does that relate to these guys over here? I mean, like, what's going on? Okay. An examination of the residuals often leads us to discover groups of observations that are different from the rest. When we discover that there is more than one group in the regression, we may decide to analyze the groups separately by using a different model for each group. So I pointed out that Mr. Adams did a thing on thermal conductivity through a phase shift. We did a separate model for each phase. Okay, so Mr. Adams did research with carbon nanotubes, and there's a linear correlation. In other words, as the temperature increases, something goes on with the thermal conductivity, and we can predict that with a linear model. But as it enters a phase shift, in other words, it goes from a solid to a liquid, that thermal conductivity or that model changes drastically. So it almost looks like a step function. It's like a step linear function. So that's what you do. And you would determine where you do that based on the residuals, okay, is what they're saying. So when we discover that there is more than one group in a regression, we may decide to analyze the group separately and use different models for each group. So here is an important unstated condition for fitting models. All the data must come from the same group. Okay? Now, it depends on the application, but regardless of what happens, if there seems to be more than one group in a cluster of data, that means something. You may not be able to use the same model. You may have to use different models, but the data is revealing. If I think that this marker is red, and then I prove that it's not red, I still learn that it's not red. Does that make sense? Same thing with the numbers. So when we discover that there is more than one group in a regression, neither modeling the groups together nor modeling them apart is necessarily correct. We must determine what makes sense. In the following example, we see that modeling them apart makes sense. Okay, just like the one that I did on thermal conductivity, that made sense to do it separately. So you can have subsets, and the subsets represent something in the data, okay? And that's what we're doing, is we're trying to make predictions about the larger population. So let's say we go back to our original project where we measured everybody's height. If you had subsets in that data, you could figure out what the subsets are. Maybe it's boys and girls. Maybe it is heritage. There are some parts of the country where people are shorter or taller than other parts, not country, the world. So there's a subgroup that you can look at the data and gain knowledge and make predictions based on the samples. So anyways, the figure shows the regression line fits to calories and sugar for each of the three cereal shelves in the market. Okay, so they've separated this into three groups. The linear model gives a predictive value for each case in the data. We cannot assume that the linear relationship of the data exists beyond the range of the data. The further the new x value is from the mean of the x, the less trust we should put in the predicted value. Once we venture to a new x territory, such prediction is called an extrapolation. Extrapolations, you got to be careful with those, okay? If I measure, let's say I compare somebody's, let's say I measure your height. If I look at all of your guys' heights up until you're 10 years old, there's going to be a linear regression. It makes sense that as you get a year older, you'll be taller. Can I predict how tall you're going to be when you're 45? In other words, will you continue to grow until you're 45, or will it taper off? Well, we know that it'll taper off, but if I look at the data and I see that there's a steady trend where you are growing every year, and I make a prediction that when you're 45, you're going to be 8 feet tall, I would probably be wrong because I don't know that for sure. So that's why we never extrapolate too far away from the mean. Extrapolations are dubious because they require the additional and are very questionable. They require the additional and very questionable assumption that nothing about the relationship between X and Y changes, even at extreme values. Okay. Well, remember the data we were looking at where it was like the household income? Remember when your homework problem where we were talking about the housing cost and income? And we saw some anomalies where people that were very wealthy didn't spend as much on their house. Well, in other words, once you get outside the data set, there might be something that changes, right? Just because you have $1 billion doesn't mean you buy $1 billion home. You might be happy with just $1 million home. Live meek and humble with your $1 million home, okay? So extrapolations can get you into trouble. You're better off not to even do them. Now, in some cases, if it's not too far outside the data set and you're aware that it could be completely wrong, it's okay to kind of ponder and think, but really there's no value in it because you don't know for sure. So let's look at some stuff here. Here is a time plot of the Energy Information Administration predictions of the actual prices of oil barrels prices. And actual prices of oil barrel prices. That seems a little redundant. How did the forecasters do? So let's look at this. So they have the actual price, that's in red, and then 98 and 99. So they have some predictions. What do you notice? Well, the predictions that go beyond are off a little bit. In other words, after two. So I think what they want you to see is the oil prices were really high here, and then this seems almost to kind of stabilize. And then you have this prediction here, and you have this prediction here. But the actual prices were much higher. So once you go beyond 2005, in other words, they made predictions in 98. In 98, they said this will be the trend. Then in 99, they said, well, it might be even higher, and this will be the trend. But even if this blue line continues forever this way, it wasn't close to what the actual price of oil was. Does that make sense? Okay. So extrapolation can be dangerous, but when the x variable in the model is time, extrapolation becomes an attempt to peer into the future. Knowing that the extrapolation is dangerous doesn't stop people. The temptation to see into the future is hard to resist. Here is some more realistic advice. If you must extrapolate into the future, at least don't believe the prediction will come true. So in 2017, if I owned a mask supply company, right, and I manufactured these masks, these paper masks that we're wearing, and I had an opportunity to buy up a bunch of supplies at a really good discounted rate, and then I made the decision, I don't make that many masks. I don't make too many of these surgical masks. I know exactly how many masks I make every year, and I supply hospitals and doctors, medical professionals, and stuff like that. I made an extrapolation in the future based on the data I had in front of me, right? But what happened in 2019? Global pandemic. So now, in other words, that can work both ways. You can overestimate or underestimate based on, and you really don't know. But now, if I look at the data of surgical mask, or even like the N95 mask over the past 2 years and tried to make a prediction 10 years from now, it might go down or it might stay up. We don't know. So we just work with the data that we have, stay within the data parameters. Anyways, outlying points can strongly influence a regression. Even a single point far from the body of the data can dominate the analysis. Any point that stands away from the others is called an outlier and deserves your special attention. These anomalies exist for a reason. Sometimes they're applicable and sometimes they're not. But if it's really far away, it has an impact on the math. So you can almost always do the math with the outlier and then do the math without the outlier. And then report that honestly. As you can see, by the late next month, you'll have over 4 dozen husbands. Better get the bulk rate on the wedding cake. So they're saying she has no husband, and then today she's going to get married and she'll have one husband, and they're making a prediction. A husband a day, basically, right? So be careful with that. That's a funny joke. So the following scatter plot shows that something is in Palm Beach County, Florida. They have the information on the presidential election. I don't know if they're saying if somebody voted for Nader, they also voted for Buchanan. I don't know. But anyways, by comparing these two parameters, by the way, these are quantifiable, right? Can you make a prediction? Yeah, the red line shows the effects of one unusual point. Oh, that's the point. We got an outlier right here. So I'm worried about trying to understand what this means. It doesn't mean anything. These are numbers. This is a parameter that has a quantitative value. This is a parameter that has a quantitative value, and for some odd reason, this number exists, this wonky thing right here. So now I can plot two trends, one that includes this dot that's clearly an outlier or an anomaly, and one that does not include it. Now, as you can see, the blue line doesn't include it. The red line includes it. So by doing both, I can make a pretty fair assessment as to what's going on. Now, I have to determine based on the information given to me, do I use the blue line? Do I use the red line? Do I make up a line in between? That's what they're talking about. So the linear model doesn't fit points with large residuals as well. And that would be a good point too. If you notice, the blue line tends to hit all these dots further over here. The red line doesn't. Because they seem to be different from the other cases, it's important to pay special attention to points with large residuals. So what they're saying is, if you were to do the residual on this red dot from here to the red line, this would be a huge residual compared to all these other dots. And if you did the residual from the red line or the blue line, clearly this is a large residual. So because they seem to be different from the other cases, it's important to pay attention to them. So the data point can also be unusual if its x value is far from the mean of the x values. Such points are said to have high leverage. So the mean is where the bulk of the stuff is usually, and once we start to get away, that distribution changes. So a point with a very high leverage has a potential to change the regression line. We say that point is influential if omitting it from the analysis gives a different model. So this is almost a different example of an outlier. So we have this one point that's really far away. The mean is right here, right? So if you look at this cluster and I have this point way over here, the trend line will have to go this way because we want to include this point. But if that same point is way down here, see how it changes the trend line from positive to negative? Because we're trying to hit that point. So we, in the same fashion, we have to determine, and by the way, the residual from here to here is probably about the same as the residual from here to here. But we have to determine how useful that information is. Okay, and this is comparing shoe size to IQ. So when we investigate, and if you think about that, they're saying as your shoe size increases, so does your IQ. But in this one, as your shoe size increases, your IQ goes down. Okay, so you got to think about that. And this person has a very large foot and an unusually high IQ, where this person has a very large foot and a slightly lower IQ, right? So when we investigate a usual point, we often learn more about the situation than we could have learned from the model alone. We cannot simply delete unusual points from the data. You can, however, fit the model with and without these points as long as you examine and discuss the two regression models. So if we look at this, and I can make a calculation with this one, I can make a calculation with this one. If I omit it, it depends on the application. If I look at this is plus or minus 20%. The majority of this blue cluster is plus or minus 20%. You have some high residuals that'll cancel with some low residual over under estimates. So I don't think that there's a trend here per se. So I would say that there really isn't a correlation or an association, right? But I have to look at all the data. So it's what we've been saying all along. Report it with it and report it without it, and then decide what's important. Influential points can hide in plots of residuals. Points at a high leverage pull the line close to them, so they may appear to have small residuals. I pointed that out. This one has about the same residual as this one does, except one's positive and one's negative. You can see influential points more easily in the scatter plots of the original data or by finding the regression model without the points. No matter how strong the association, no matter how large the R-squared value, no matter how straight the line, there is no way to conclude that from a regression alone, one variable causes the other. Okay. And even if we make a prediction, it doesn't guarantee that it's, even if you have 100% regression, in other words, your R squared value is 1, and then your correlation would be a positive 1. That means every point is on the line of regression. Well, that doesn't mean if I go out in the real world that that'll be the case every time. So that's what they're saying. We're just guessing, basically. With observational data, as opposed to data from a design experiment, there's no way to be sure of some lurking variable is not the cause of any apparent association. Okay. So the following scatter plot shows that the average life expectancy for a country is related to the number of doctors per person. That makes sense. The more doctors you have, the longer people live. This is a scatter plot that shows that the average life expectancy for a country is related to the number of televisions per person. So what we're talking about is resources, right? If you have more money, you'll have more doctors, more education, the more developed the country is. Well, the more developed the country is, the more TVs you have. So what they're saying is you could argue that you just need to buy a bunch of TVs for third world countries and they'll live longer. Okay. So since the televisions are cheaper than the doctors, send TVs to countries with low life expectancies in order to extend lifetimes. No. How about considering the lurking variable? Countries with high standards of living have both longer life expectancies and more doctors and more TVs. They have more resources. If higher living standards cause changes in these variables, improving living standards might be expected to prolong lives and increase the numbers of doctors and TVs. It's not the doctors so much as it is medical treatment. Right? You can have every person can have their own individual doctor, but it's the medicine and the nutrition and the access to clean water and being able to sanitize. Those are the things that make you healthier. So one parameter doesn't necessarily mean anything. Although I find it interesting, look at the doctors per person versus life expectancy and look at the TVs. The TVs appear to have a tighter correlation. If we were to look at the residual plot between this and the residual plot between this, I bet you this R value, the correlation coefficient, and the R square value would be closer to 1 than this one. So in other words, TVs are more impactful than doctors according to this data. So scatter plots of statistics summarized over groups tend to show less variability than we would see if we measured the same variable on individuals. This is because the summary statistics themselves vary less than the data on the individuals do. So there is a strong positive linear association between weight in pounds and height, right? So if you're taller, you're obviously going to weigh more. Except for this guy, he weighs way more than most of these people at this height. Instead of the data of individuals, we only had a mean weight for each height. We would see an even stronger association. So what they did is they took this data and they said, well, what's the mean for somebody that's 72 inches? What's the mean for somebody that's 70 inches? What's the mean for 69, 68? And when you plot that, you have a tighter association. Okay. So means vary less than individual values because we're kind of finding the center of the individual's values. Scatter plots of the summary statistics show less scatter than the baseline data on individuals. This can give a false impression of how well the line summarizes the data. There is no simple correction for this phenomenon. Once we have summary data, there's no way to get back to the original values. Okay, so whenever we do stuff, and I don't know if you guys are going to do research or collect statistical data for the rest of your lives, but if you do, keep all the original data. No matter what summary you do, just keep the data, never lose the original data, because you can go back and look at it a gazillion times. So make sure the relationship is straight. Check for the straight enough condition. Be on guard for different groups in your regression. If you find subsets that behave differently, consider filtering a different linear model for each subset. Don't do a whole lot of extrapolation. right? A lot of textbooks say don't do any at all. And beware of extrapolating into the future. We don't know. Heck, we also found out that unusual points always deserve attention and may reveal more about your data than the rest of the points combined. Beware of high leverage points, especially those that are influential. Such points can alter the regression model a great deal. And consider comparing to regressions. Run regressions with extraordinary points and without, and then compare the results. Treat unusual points honestly. Don't just remove the unusual points to prove something. Okay. Beware of lurking variables. Don't assume association. So even if we follow all these extra rules, even if you have a good fit, it doesn't mean that there's a cause. Right? TVs don't cause people to live longer. All right. Watch out when dealing with the data that are summaries. And summary data tends to inflate the impression of strength in the relationship because you're centralizing and standardizing everything. So try to keep the original data. And then there are many ways in which the data set may be unsuitable for regression analysis. Watch out for subsets in the data, examine residuals, and recheck the straight enough condition. The outlier condition means two things. Points with large residuals or high leverage, especially both, can influence the regression model significantly. Perform regression analysis with or without such points to see their impact. Even a good regression doesn't mean that we can believe the model completely. Extrapolation far from the mean can lead to silly and useless predictions. An R-squared value of nearly 100% does not indicate there is a causal relationship between X and Y. Remember the TVs increasing life? No. Life expectancies. Watch out for regressions based on summaries of data sets. They appear to be stronger than what they actually may be. On the AP exam, be prepared to read regression output without an outlier. Read carefully to see if the slope has changed. In other words, they might give you data sets and have one with an outlier and one without the outlier, and then you have to answer a question or prompt, what happened. So what they're saying is look for changes in the R-squared value. Okay, that outlier can have a huge impact on R-squared. Remember that some influential points have small residuals. When we were looking at the shoe size compared to the IQ, those two influential points had the same residual, except one was positive, one was negative. Completely changed the correlation. One was positive, one was negative, but the residual was the same.